Okay, B equals K infinite minus 1 divided by L square. So this is the basic definition of buckling. And when we expand the meaning of K infinite eta F, we can write eta F minus 1 divided by L square. Then we can write in as the above form. Critical buckling square is eta, instead of eta F, we can write nu sigma F divided by sigma A, and minus 1 divided the definition of L square, D minus sigma A, right? So this is the equation, basic equation. B square is sigma F sigma A minus 1, and D divided by sigma A. Now, let's focus on the right-hand side of this equation. The right-hand side is nu sigma F sigma A D. So we have 4 parameters in the right-hand side. So nu is determined by material. So uranium, plutonium, radium-235, radium-233, we know the nu. Okay. Sigma F can number density of fuel multiplied by microscopic cross-sectional fission, sigma F. And also sigma A is the number density and absorption cross-section, and D is diffusion coefficient. That means the right-hand side is determined only by material property. So when we know the number density and material, then we can calculate the right-hand side. Done. Left-hand side, let's review the table 6.2, buckling. So for infinite slab, buckling was pi divided by A, parallel piped, pi divided by A squared plus pi divided by B squared plus pi divided by C squared. For infinite cylinder and sphere, pi divided by R squared. So from this table 6, we can see the buckling is determined by geometry. Okay, geometry. So when we know whether it is cylindrical parallel pipe or rectangular parallel pipe, infinite cylinder, finite cylinder, slab, we can determine buckling by geometry. And completely differently, left-hand side is determined by geometry and right-hand side is determined by material property. Completely different dimension. We cannot compare mass with length because they are different dimension. Mass, length, this different dimension, right? So in this equation, critical buckling equation, left-hand side is determined by geometry and right-hand side is determined by material property and number density, right? And when these two values are equal, then we can say the reactor is critical, right? So when this is important, you know, this expression in English conversation, when someone say like this is quotation mark. So that means this is important. So when the left-hand side and right-hand side is the same, we call it critical. So the definition of critical is neutron observed in one generation is the same as neutron generated in the preceding section. So the number of neutrons is maintaining. So number of neutrons is the same regardless of time. We can say critical. If the number of neutrons is increasing, then we call supercritical. And number of neutrons is decreasing, it is subcritical. So it is important to determine when it is critical. Left-hand side and right-hand side is the same. then it is critical. So this is physical meaning of critical buckling, and this is very important because, okay, when we know the material composition, then we can determine right-hand side. Right-hand side does not include information regarding geometry. Okay, so when we know the material property, then right-hand side is determined. Then, if it is sphere, for example, sphere, BC square will be pi divided by R square. For example, if it is square, and RC can be determined by the right-hand side. Okay, so when we know the material property, we can determine the size of the reactor for criticality from this equation. And also, when we already have the geometry, left-hand side is determined, then it's a little bit more complex, but we can determine the material composition. So this is firstly very important, and concept is quite meaningful. And also, one very important thing to you, not to me, is it is quite easy to make problem utilizing this equation. So, for example, when I give you material property and I ask you to determine the size of the reactor, the problem is quite straightforward. So that means you will probably see problems utilizing this equation in the entrance exam of the graduate school or entrance exam of the Korea Hydro and Nuclear Power, and or when you have to undergo a national exam for nuclear engineer. So in any kind of nuclear engineering test, you can see this problem because this is quite meaningful and quite easy to make problem because it is straightforward. There's no other definition. So that means it is quite important. Okay, actually I'm saying everything is important, but believe me this time. Now, this equation is the definition of buckling when we derived the reactor equation. The only difference is B1, that is fundamental fundamental buckling. So the buckling you saw in the table 6.2. And from this, as you say, when you know the critical size, you can determine critical mass. Or when you know the critical mass, you can determine the critical size. So I already mentioned that. But we have here a critical mass. What is critical mass? 임계질량, critical mass. So in order to make some nuclear reactor critical, you must have certain mass or certain size. So that means in order to make atomic bomb with uranium-235 or plutonium-239, when you make atomic bomb, there is a concept like critical mass, 임계질량. So if the mass is smaller than the critical mass, you cannot make atomic bomb. Okay? So, and you cannot make reactor critical with less than critical mass. That means this reactor battery that isn't possible. That isn't possible. So we need certain size to make reactor critical. So small reactor is possible, but this small we cannot. There is concept like critical mass and critical size. So the reactor should be larger than critical size, and the reactor should be larger than critical mass. Okay. Now, this is an example. So I normally I don't deal example, but this time let's deal with this example. A fast reactor assembly consisting of an homogeneous mixture of plutonium-239 and sodium to be made in the form of bare spherical reactor. The atom density of these constituents are: fuel density is 0.00395 10 to the 24, and for the plutonium, and Ns for sodium, it is 0.02234 times 10 to the 24 for the sodium. Estimate the critical radius of the assembly. That means we have to calculate the right hand side first and then get the value for the radius. But anyway, when for the critical equation, this is the spherical reactor. So that means the buckling is pi divided by r square. So you can substitute to that equation and rearrange the equation with respect to RC. Then you can get this expression. Now you solve the right hand side and you get RC. That's it. So in order to calculate L and K infinite, then you have to know the efficient cross section. So sigma AF is what it says, number density divided by absorption cross section of fuel, 0.03395, that is given, and 10 to the 24 is cancelled out with 10 to the minus 24, so 2.11 bar. So you get sigma AF, and sigma AS sodium is 0.02234 times 10 0.0008. Then you get sigma AS, and total absorption cross section is adding up together. And the thermal utilization factor F is total sigma AF divided by sigma A is nearly 1. So absorption cross section of sodium is quite small. Okay, so thermal utilization factor is nearly 1. That means absorption cross section of sodium is quite small. And K infinite is eta F. You can find a lookup table and you get eta, and F you just get it. So 2.61. And in order to calculate L, you need diffusion coefficient. And diffusion coefficient is 1 over 3 transport cross section. We just briefly learned. So we just know the equation. I didn't deal that in detail, but you know we did this equation, and you can calculate that with macroscopic transport cross section. So this 1 over 3 macroscopic transport cross section you get from table 6.1, and then you get macroscopic transport cross section of plutonium and sodium. Now you get diffusion coefficient. And as to the extrapolated distance, d is 2.13 d. That means 6.84 centimeter. Now, anyway, the L square is d minus sigma A. That means 3.21 divided by sigma A, 0.0835. And you get L square 384. Now you substitute everything to the equation, and then you get RC is 49.5. You have to subtract extrapolate distance from the RC. So RC is RC tilde minus D is 42.7 centimeter. Not difficult. Not very difficult. So in the criticality buckling equation, when we know the material property, we can calculate the right-hand side, and then we calculate RC. And in this example, we didn't read the value of D from the lookup table. Instead, we calculated D from the value of transport cross-section, 1 over 3 sigma TR. That is one thing. And second thing is, when we calculate the RC tilde, this is a wave, but we call it RC tilde, T-I-L-D-E. So RC tilde. So critical radius RC equals RC tilde minus extrapolated distance D. That is 2.13 diffusion coefficient. Okay, so we get 42.7. So with this kind of material property, the reactor size should be at least larger than 42.7. So let's review the example again. Now, the reactor is plutonium-239 and sodium. Homogeneous mixture. Homogeneous mixture means 균질한 혼합물. 완전히 가루로 만들어가지고 균질하게 섞어놨다고 가정하는 게 homogeneous mixture입니다. 아주 골고루 섞여 있는 거예요. fuel과 그 소디움, 나트륨이 골고루 섞여 있는 거예요. 가상적인 거죠. Now, this is a homogeneous mixture of plutonium-239 and sodium. That means we don't have moderator. Okay, so sodium is coolant for the fast reactor. So this is kind of fast reactor, not thermal reactor. It uses fast range of neutron. Anyway, fast neutron and fuel and coolant sodium is mixed together, and this is a spherical reactor. And in order to make the critical, the size of the bore is should be larger than 42.7 centimeter. That is the result. So when we make the atomic bomb, we calculate the same way. Of course, there is a difference. For example, when the plutonium is pressed, then the pressure is different, and the sigma value will be different. So we have to know the exact sigma value for certain pressure. So normally in the uranium bomb, the sphere is separated into two, and when we need to explode the atomic bomb, we just add it together to become a critical mass. So the sphere is a half sphere and half sphere is separated normally. Then it is less than the critical mass, so it does not explode. It does not undergo criticality. But when we need to explode this, we just add it together and attach it. Then it reach a critical mass and become a bomb. The point is, we would like to explode that at certain time. The timing is quite difficult. And also for the plutonium bomb, we have this kind of sphere. It is actually below critical mass during the atmospheric pressure so less critical mass at atmospheric pressure. But when we would like to explode this, the surround of the sphere is TNT. So we explode the TNT to give the pressure in the sphere, and then at the high pressure time, the plutonium reach criticality because the sigma F will be different at high pressure. So this is the theory of plutonium atomic bomb, and uranium-235 atomic bomb is half sphere divided, and then we add it together when we would like to explode this. So anyway, this criticality calculation is useful for reactor and atomic bomb anyway. So this is a basic element nuclear engineers should learn. Now, uh, let's look at the bottom first. B equals K infinite minus 1 divided by L square. Definition of buckling, right? So we multiply L square to the both sides, BL square, and 1 in minus 1 in the right hand side move to left hand side, and 1 plus BL square, B square L square, and then divided it with K infinite. Then we get the above equation. So K infinite divided by 1 plus B square L square. Now, K infinite. What was K infinite? K infinite was a multiplication for the infinite reactor. Infinite reactor. In the infinite reactor, there is absorption and fission, but there is no leakage. Okay, and let's review the meaning of 1 divided by 1 plus BL square. So when we use the definition of L square, we can make that sigma A divided by sigma A plus B square D, right? Now, what was B square? B square was Laplacian, right? Laplacian. So that means when we multiply flux to the denominator and numerator, then sigma A phi means absorption, and in the denominator sigma A phi absorption, and B square D phi means leakage, right? So 1 plus, that means sigma A divided by sigma A plus B square D is actually denominator means absorption and leakage divided by absorption. That means this term is non-leakage probability. Non-leak 1 divided by 1 plus B square L square is non-leakage probability. So the expression K infinite divided by 1 plus B square L square is a multiplication factor for finite size reactor. K infinite is for the infinite reactor, but K infinite divided by 1 plus B square L square is multiplication factor for finite reactor. So 1 divided by 1 plus B square L square is non-leakage probability. That is one thing, non-leakage probability. K infinite, multiplication factor for infinite reactor. And K infinite multiplied by non-leakage probability is K for finite reactor, multiplication factor for finite reactor. Let me say again. First, 1 divided by 1 plus B square L square is thermal non-leakage probability. Non-leakage probability. Second, K infinite is multiplication factor for infinite reactor. And K infinite multiplied by non-leakage probability is multiplication factor for finite reactor. Okay, that's important. Uh, I don't want to go further today, and I would like to ask you to review the example again and using your hand to calculate it. It is not homework, but you will do that, please, because next time we will apply the same philosophy to a little bit more difficult problem. So you have to be ready yourself for the next lecture. Okay, so I ask you to be familiar with the equation, practice example, and guess what? Guess what? Okay, read the textbook, please. Okay, let's call it a day. Bye bye.